Hi, in this video I'll demonstrate programming an analog computer. I think this will highlight some of the fundamental differences between an analog computer and a digital computer. In the interest of time, I'll have to gloss over and actually skip some of the preliminary steps in programming the computer. Here I'll just show the physical programming of the computer. In a later video I'll cover the aspects that lead up to the physical programming of the computer, which are very important but a little complex. Programming an analog computer is done through the patch bay. That's the first fundamental difference you'll see between an analog computer and a digital computer. Programming the analog computer basically consists of interconnecting the internal computing elements to solve the problem at hand. The computing elements are generally amplifiers, and in fact the operational amplifier used in electronics today has its origins in the analog computer. The analog computer I'll be using for this demonstration, the COMDYNA GP6, has the patch bay here on the left. The patch bay is a little intimidating at first, but it's pretty straightforward once you understand the layout. There are 4 integrating amplifiers, and these are here, 1, 2, 3, and 4. Those are capable of performing mathematical integrations. They have various inputs for various amplification, and they have initial condition inputs. So if you remember from calculus, you always need a constant of integration when you solve an integration problem. So the initial condition allows you to input that constant of integration. Additionally, there are 2 summing amplifiers, 5 and 6, so those don't have the integrating capacity, but you can use those to sum various voltages. There are also 2 inverting only amplifiers down here at the bottom, 7 and 8, so a total of 8 amplifying elements, 6 of which can be used as summers, and 4 of the summers can also be used as integrators. There are also 2 multiplying elements which aren't numbered, just 2 separate multipliers here, which are very handy for solving some differential equations. Across the top are convenient reference voltages. Those allow you to tap the internal power supplies in setting up your parameters. There are 6 potentiometers with fixed grounded bottom ends for applying a gain of less than 1 to any voltage. Additionally, there are 2 potentiometers, 7 and 8 down here, which have a floating bottom end, and you can tie separate voltages into the top and bottom of the potentiometer. We won't use those for this demonstration. The preliminary steps of programming an analog computer generally lead to a diagram to allow you to program the computer. Even the simplest problem is going to be fairly complicated to hook up the interconnect in the patch bay. So I typically, with the COMDYNA GP6, I use an illustration out of the manual in order to set up the function of the analog computer. This allows you to quickly wire up the individual computing elements through the patch bay and eliminates some of the mistakes that might be made. The problem I'll be programming today is what I refer to as the vertical projectile problem. The specific problem came from a book titled Analog Computer Simulation of Engineering Systems by M.L. James, G.M. Smith, and J.C. Wolford. This is adapted slightly for the COMDYNA GP6. In the interest of time, I won't go into the details of where some of these values come from in this demonstration, but you should be able to follow along with the solution of the problem. It's a basic physics problem, very basic physics problem. It's usually one of the first problems you'll see in any classic physics textbook. And it also is an interesting mathematics, particularly calculus problem. Now typically in programming the analog computer, one would wire up the patch bay before energizing the computer. I will start up the computer a little early so you can see some of the effect of adjusting the controls. But before I energize the computer, I'll go ahead and jumper out some of these controls so we don't go into overload on initial power up. Some of the connections I did not mention in the earlier description are the SW and OP connections. Those aren't well described in the manual, but I believe that stands for switch and operate. I believe those would be used to control the timing of the integrators through an external source, but we won't need those in this demonstration, so I'll just jumper those out. Also, each of the amplifiers should generally have a feedback loop connected in order to prevent overloads. So I'll go ahead and temporarily insert a jumper to connect all the feedback loops so we don't go into an overload. Now I should be able to energize the computer, and I'll go ahead and turn on the oscilloscope, although we won't see a display for a while. So in the problem, the first parameter we need is the acceleration due to gravity. This will be considered a negative value for the problem since the acceleration due to gravity is in a downward direction, and for the problem I'll define up as the positive y-axis. So I'll use the negative reference voltage, and it's conveniently located above pot 2, so I'll start with that potentiometer. And then in order to be able to visually see the value for the acceleration due to gravity, I'll connect that to an op amp, one of the inverting op amps that is unused. That would typically be a waste of resources in an analog computer, but I have the amplifiers to spare, and it would be interesting to be able to see that value on the oscilloscope for this demonstration, so I'll go ahead and use that. We can set the acceleration due to gravity by switching to pot set mode and selecting channel 2. The scaled value from the problem would be 0.161. This just sets it to essentially 16.1% of the reference voltage, and that will be 1.61 volts. I'll get into more of those details in a later video. In order to see the acceleration due to gravity, I'll have to use amplifiers 7 and 8. We'll start by connecting the wiper arm from potentiometer 2 to the input of amplifier 7. Now you may have noticed the meter immediately changed from my setting of 0.161 now to 0.152. That's actually an error. I did that on purpose to demonstrate you really want to set up your interconnects before adjusting the potentiometers, because the computing elements of the analog computer will load down the potentiometer. So the earlier setting I made was incorrect because it did not take into account the load of the amplifier. So that's simply corrected by readjusting it once the computing element is connected, back to our value of 0.161. Now, amplifier 7 is an inverting amplifier, but I actually would like to see the negative going acceleration due to gravity. So I'll have to perform another inversion, and since amplifier 8 is not in use, I'll go ahead and use amplifier 8 to provide the second inversion. Now if we switch over to operate mode, we can actually see that voltage on channel 7 is the inverted acceleration due to gravity, and then channel 8 is the acceleration due to gravity. The acceleration due to gravity will be the input to the first integrator. To solve the problem of position of the projectile, we need to actually integrate the acceleration to determine the velocity, and then further integrate the velocity in order to find the position. We'll take the acceleration due to gravity at amplifier 8 output and apply that to the input of amplifier 1. But amplifier 1 will actually be configured as an integrator. So I'll switch this jumper that I inserted originally down to the integrating input so it has a capacitor in its feedback, and then we can connect the acceleration due to gravity into that amplifier's first input. Now we can switch to operate mode again, and you see we are going into overload. When I look at the output of the integrator, integrating the acceleration due to gravity into the velocity function, you can see we're going off scale here, so that's the reason for the overload. The reason for that is I have not yet set up the initial condition for that amplifier. So let's do that now. I'll go ahead and go back to pot set mode. Again, just so that I can see the velocity on the oscilloscope, I'll go ahead and use a couple of amplifiers in order to bring that out to the oscilloscope. The scaled version of the velocity for this problem ends up being 0.644 positive. It starts with a positive initial velocity heading in the positive up y direction. So I'll use channel 1 since it's conveniently located under a positive reference, and we'll connect the wiper of channel 1 to the input of amplifier 5, and it will simply be configured as an inverting amplifier with a gain of 1. So I've already set this potentiometer in the setup for this problem. It's actually set to 0.644, so that would be set through this dial here. And because I waited until I had the load connected to the wiper, we get the correct value. Now we do need to invert that a second time, so I'll go ahead and connect the output of amplifier 5 to the input of amplifier 6. Those are both unused for this problem, so I can go ahead and take advantage of those. And now the output of amplifier 6 can go to the initial condition for amplifier 1. So that sets up our initial velocity for the projectile. Now, if I switch to operate mode and look at the output of channel 1, the output of amplifier 1 is the integration of the acceleration due to gravity with the initial condition, but since every element in the analog computer has an inverting function, it's in the wrong direction. So this makes it appear that we start with an initial velocity in the negative range and the acceleration will cause it to go positive. Now that isn't really a problem for the solution to the problem, because we also get an inversion when we integrate the velocity for the position function. But for the purpose of display, it would be convenient to see this in the proper polarity. So I'll take the output of channel 1 and apply that to the input of channel 3. Now when we look at amplifier 3's output, we see the proper orientation of the velocity. It starts at a positive initial velocity and then goes in the negative direction due to the influence of the acceleration due to gravity. The next step is to integrate the velocity function to provide the position function. The initial condition or initial position is actually 0, so we don't have to have a connection to the initial condition jack of the integrator for the position function. But there is some scaling required, so I'll take the output of amplifier 1 and place that to the positive connection of potentiometer 3, but we will configure amplifier 2 as an integrator. Then I can bring the potentiometer output of 3 to the input of amplifier 2. Now if we look at amplifier 2 output, we actually have the position function and our problem is solved. Now with the problem solved, we can go back through and look at the various parameters of the problem. On amplifier 8's output, we have the negative 0.161 scaled representation of the acceleration due to gravity. Then on channel 6, we have the positive 0.644 scaled version of the initial velocity. Those two voltages are input to amplifier 1, which integrates that, so it integrates effectively the scaled acceleration due to gravity with an initial velocity. And the output is seen at amplifier 3 in the inverted version. So we have the positive initial velocity, which immediately begins to go towards the negative direction due to the negative going acceleration due to gravity. This is slowing down the object as it moves up for the first 4 seconds until the velocity actually reaches 0 at 4 seconds. Then the object will come down and the velocity is changing at the same rate, but it's now negative, so the object is heading back towards the Earth. And then on channel 2, amplifier 2 output, we have the actual position function. So this is the integral of the first order function of velocity, so we get the second order parabolic function. So this was a brief demonstration of programming a simple problem in an analog computer. Back in the 50s and 60s, analog computers used in industry were much more complex. I've read articles about analog computers with over 500 operational amplifiers and a corresponding number of potentiometers and multipliers and even external function generators. Programming a system like that would typically require months to work out all the differential equations and scale the problem for the analog computer and then figure out the interconnection. So it was definitely a non-trivial task, but this was used very effectively to solve a wide variety of engineering problems, everything from missile trajectories to aircraft simulation to automobile suspension and a huge variety of other problems. So I hope you found that interesting. I'll continue to put together some of these videos to get into a little more depth on the operation of the analog computer. Thank you for watching.